Hello, in this lesson, we're going to we've been summarizing for our functions periodically, but this time we're going to do a summary for all of the functions we have studied since the first constant functions. And if we look back, we have covered the concept of function. We talk about that a function is a rule that assigns to each input, right? Whatever that input, it could be X. Initially, we used X, exactly one output, f of X. And for each input, there's exactly one output. So that's the fundamental requirement of function, okay? So we have done this flowchart, and we understand for each rule, it determines the domain and range. And then we talk about one-to-one function. And we talk about the definition of one-to-one function, right? And its important properties. So if a function is one-to-one, it has a unique inverse. So let me make sure you can see this negative sign there. Okay, F inverse. So if it's a one-to-one function, it has this property. We have applied this property to numerous cases where a function has an inverse, has exactly one inverse. And we also talk about if a function is not one-to-one, which is if a function is not one-to-one, for some different input, the outputs are the same. And then we talk about increasing function as a definition, increasing function on an interval, or decreasing function on an interval. So we talk about these definitions. And then we talk about even function, odd function. And let's look at what are the functions we have studied. We study these functions by groups. The first group are these 8 functions, right? Constant function is the simplest linear function, and x to the power 3, and cubic root function. And we talk about their domain and range, okay? And square function, which is the simplest quadratic function, the absolute value function, which we have a very specific lessons on absolute value and its properties. Very, very important. Okay, we gotta, we'll come back to it, again and again. Square root function, and reciprocal function, okay, 1 over x. So for each input, the output is 1 over x. And we have explained the fact that for each one of the graph, okay, we have this feature. Okay, for each one of the graph, right, the input, I'm going to use green, right? So this is the input, and that's the output, input, output. And the input is horizontal measurement. Input is the horizontal measurement for all of these cases, okay? Input. And the outputs are vertical. It's just different rules produces different outputs. Different rules produce different outputs. So inputs, output, input, output, input, output, input, output, input, output, and keep going. This concept, this visual creation, okay? Input, input, okay? Input is horizontal measurement from the origin. Output is a vertical measurement from the origin. Output. The only thing that's different is the rules are different. The rules are different. Okay, input, output. Okay, visual, algebraic. Okay, and after this part, we continue to study the, we also discuss some, extreme cases like horizontal asymptote, vertical asymptote. Here, we're not going into those details. Make sure you go watch those lectures where we did it. Exponential and logarithm. Okay. By the way, for all of these functions, for the first group, we studied whether they are one-to-one, right? We studied whether they're one-to-one. If it is one-to-one, what's the inverse? And what is not one-to-one? How we make that statement is not a one-to-one. Increasing function or decreasing function, and in what interval? Even function or not, odd function or not, or either. Okay, so we discussed all of these concepts as they're applied to those 8 functions, and then we studied exponential function and logarithm function. We study them as pairs. Exponential, logarithm as pair. Okay, we learned that they're not only they are, they're all functions, they're one-to-one functions, and they're inverse function to each other. And it has that nice property that all inverse pair have, which is symmetrical along the green line. Along the green line. One's domain is the other's range. Okay, so we studied these. And we study these for base 3. And in comparison, right, what's the relative position between base 2 and base 3? And finally, we get to base E, which is one of the most important exponential and logarithm functions you're going to use in your future calculus classes. So for these functions, we studied whether it's increasing, decreasing, and so on and so forth. So we studied all of these concepts, right? Even, odd, and so on and so forth. And finally, we spend a lot of time studying trig functions. We talk about the 3 pillars of trigonometry. 3 pillars of trigonometry. A is for angle measurement. Positive angle are measured counterclockwise from the standard position. Negative angles are measured clockwise from the standard position. And we talk about, and this angle measurement is very much related to the input for all of these functions. So the input to all of these functions are measured according to these rules. Okay, and then the output for all the arc functions, the output for all these arc functions are also measured by these rules, by the rule of the angle measurement. Okay, and the input for sine, cosine, tangent, cotangent are angles, and the output for the arc functions are angles, and the output for sine, cosine, tangent, cotangent, secant, cosecant are ratio, and the input for the arc functions are ratio, and the output, of course, are angles. Reference angle. So we talk about the definition of reference angle. Reference angle is the positive acute angle between the terminal and x-axis. And then it's a definition. If A is an angle in standard position and xy is any point, okay, any point on the terminal side of the angle other than the origin. which this guarantee that R is going to be positive, and we define the 6 trig functions. All right, so let's review what are we seeing by these functions. Sine function, right, as a sine ratio. So input is angle, output is sine ratio. And in this graph, we have that unit circle we're pretty familiar with. But on this graph, the input, okay, we can also use the green. The green here, we kind of use the gold. Okay, so input, output. Output is a blue. The blue number refers to the blue number on that specific unit circle. And I hope you guys know what I'm talking about. Okay, so just to make sure, I'm going to bring that unit circle with us. Okay, just to make sure we are clear about what we are talking about. Okay, so that unit circle. So all those blue numbers. Okay, all those blue numbers. Okay, all the blue numbers. And the red numbers, that's of course for cosine. Okay, of course that's for cosine. Okay, the making of the curve, input, output. You see, input, output the same way as we saw at the picture for the other functions we did, right? Tangent is a tangent ratio y over x, and cotangent is that ratio x over y, x over y. Okay, so this is the cotangent. So I put all of these curves here. We've done all of these curves from negative 2 pi to 2 pi, except we didn't do as much for secant and cosecant, but they are at our fingertips, aren't they? So for cosecant and secant, we have the curve and the meaning are the same, input, output, right? Input is the angle, the output, or arc length, the output are the ratios of the specific function. Okay, so for cotangent, of course, is x over y. So that's, we use this color. All of these have the same input, which are angles. Okay, that's input, input, output. Cosecant, okay, cosecant. Now, with that said and done, let's look at their domain and range. Let's look at our domain and range. Okay, I would like you guys to work with me when we review these very important concepts. We're going to apply them momentarily. Okay, we're going to apply them momentarily. So let's look at the domain. Okay, domain and range for sine is -1, smaller than or equals to sine of A, less than equals to 1 for any real number. For any real number, which belongs to from negative infinity to positive infinity. Okay, so that's one version of the domain and range. Okay, and I think I can do, I'm going to give you a couple versions of it. Okay, I'm going to give you a couple versions of it. And the next version, of course, is the absolute value. The absolute value, which you're pretty familiar with. Okay, we talk about these multiple times. For that, wait. I should go here. Wait, sorry. There, okay. And the last one, of course, is that interval form, okay. The interval form, as we talk about, is the least useful. It's the least useful. It is still useful, but it's the least useful algebraically. Okay, and for cosine, domain and range are the same. Domain and range are the same. Tangent, right? Tangent, domain and range. Domain, okay, determined is determined by the denominator cannot be 0. So x cannot be 0. So when we look at these, when we look at the unit circle, and we notice where the x is equal to 0, right? So these are the two terminals where the x's are equal to 0 on the y-axis, right? Positive direction, negative direction. So we talk about that. So the domain is x, well, the angles can be any real number other than odd number multiples of pi over 2. Okay. And the range, right? So this is the domain. And the range is all real numbers. We have discussed in great details why it is so. For cotangent, denominator is y. Therefore, whenever y is 0, where we have these two cases, when the terminal is on the standard position or the opposite direction, overlapping with direction of pi, those cannot be in the domain. Those cannot be in the domain. So for the domain, okay, cotangent's domain is the angle cannot be any multiples of pi. Cannot be any multiples of pi. K are any integer. K is any integer. Okay, so we specify that K. Let's see, where's my tangent? Right, so right here. Okay, K is any integer. So these are about the domain and range of cotangent and tangent. And now comes the secant. Secant has the same domain as, but secant's range has two different forms. It's either less than equals to -1 or greater than equals to +1. And another form would be the absolute value of it is at least 1. Okay, and cosecant is almost similar, except the domain is, it cannot be multiples of pi. So the domain of cosecant is the same as the domain of cotangent. The domain of secant is the same as tangent. We didn't graph everything for secant and cosecant. They're at your fingertips, but you can graph them if you want. And if you have any questions, feel free to let me know. If we have time later in the semester, I'll arrange some time to do something about these graphs. Okay. So we have summarized about all of these functions, right? 1-to-1 or not. None of these are 1-to-1, okay? But we use truncation method. We use truncation method to create arcsine, arccosine, arctangent, and arccotangent. So let's look at these arc functions. The notation of these arc functions, we've been using those classic notation. We've been using those classic notation. Okay, so for arc function, if we look at the, okay, so I'm going to set up a table, which we don't need so many rows. Okay, so these are arc functions, right? We have some detailed studies. So here I'm not going to repeat all the details, but just as much as we can, right? So arc sine, okay. Arc sine is also known as AKA as arc sine written this way. It's not, doesn't mean it's a universal sine. It just means it's the same as arc sine. So when you read it arc sine. Okay, so X is a ratio, and the rule of the functions is such, okay, and the output are angles, the output at angles. And this ratio is between -1 to +1. Okay, so the domain is from -1 to 1, and the range is from -π/2 to π/2. π/2 to π/2. The graph is at our fingertips, really. Okay, but I'm going to, I think I bring that picture along with us. Okay, I bring that picture along with us, which is this picture, the purple one, okay? So we have a sense that we've done that, because that was a picture we worked with. On the unit circle wise, okay, I'm not going to draw the unit circle, but I'm going to draw something. I'm going to draw something like this. I hope you guys will understand what I'm saying. It's the rectangular system. It's the rectangular system. Which quadrant is left? Okay, so from the definition's perspective, so when arc sine is considered, right? When we look at ARD, right? And we know there are two quadrant were chopped off. So I'm going to put that picture in the table. And I hope you guys will draw it. Okay. In the case of sine, I'm going to put it this way with a truncation. So the quadrant 2 and quadrant 3 are truncated, chopped off. Okay. So what I would do is I'm going to put that truncation out there. Okay, so please do the same. And I'm sure you understand what I'm talking about. So, and on the domain and range part, I think I'm going to just condense it a little bit. So here, I'm going to wait. So here, yes, that will work. Okay, so I'm going to put that the domain belongs to that the range, right? And this indicates the range. That's one way to express it, right? So this way we'll have a more condensed form. And you know, this, the purple is the arc sine. And also there are other forms for the domain, okay? So the absolute value of x has to be less than equals to 1. And arc sine, okay, arc sine, or the other one, right? The absolute value is less than or equals to pi over 2. So all these are different forms of expressing domain and range, okay? And you can be, it can be expressed mixed or the other. So I'm giving you all of these different forms, okay? And the arc sine is between negative pi over 2 and less or equal to pi over 2. Okay, so that's the different forms, right? Interval form, domain range, interval form, the absolute value form, and interval form for inequality form for domain and range. For arc cosine, okay, for arc cosine, so arc cosine, it takes ratio, okay? So we still have this other form of writing arc cosine, but you read it as arc cosine. Domain and range wise, and let me see if I think I have that. I do have that form with me. Right here. Okay, this is my arc cosine. So that's the red. That's the red. You have seen this all along. It just now you see them together at one place. Okay, and in terms of the quadrants, in the arc cosine case, okay, we only have quadrant 2 and quadrant 1. Okay, quadrant 2 and quadrant 1. So when we chop it off, right? So when we chop it off, so we're going to chop off quadrant 3 and quadrant 4. Okay, so we're going to quadrant 3. Quadrant 3 and quadrant 4. And this is going to be the quadrant for arc cosine. Okay, so in other words, domain and range are determined by this rule, arc cosine. And let's see what the domain and range. Domain range, I'm going to use a comparative way to show you, right? Domain are the same, but range are not. Okay, so from 0 to pi. Okay, domain the same, arc cosine. Arc cosine, actually, its absolute value form is this. Okay, I never actually talk about it in class. Okay, you know, take it as if you wish. If you have any questions, it will give you the same thing. It will give you the same thing. And the other form is from 0 to pi. It's not likely I'm going to test you about it, but if you really want to know the absolute value form, and this is the absolute value form. Okay, so that's the arc cosine, which is arc cosine. okay? Now, arctangent. Arctangent has another form that was written. It means arctangent, means the same thing, okay? It meant the same thing. It takes the ratio, produces angles, okay? So that's arctan and produces angles, okay? And these angles, okay, so I'm gonna show it to you. In terms of domain and range, okay, in terms of domain and range, of course, this can also be arctan. You read it as arctan. You read it the same way. You read it the same way. Domain, this guy, domain is all real numbers. Negative infinity, positive infinity. And the range in the interval form is in negative pi over 2 to positive pi over 2. Positive pi over 2. And the absolute value form, right? For the interval, x is going to be just like that, right? The absolute value form for arctangent. In absolute value form, the range expression is less than pi over 2. Less than pi over 2. And last, the range is, you actually don't need this because it's all real numbers, right? We don't really need this. So it's negative pi over 2 to pi over 2. Okay, and that's less than arctan and less than pi over 2. So this is arctan. Its graph, of course, is most familiar. So let's look at, I'm gonna put this on the quadrant part. Okay, on the quadrant part, it's actually the same as sine. It's the same as sine. You just cut off the second and third. Okay, curve wise. Okay, curve is easy to get. So arctan. Okay, arctan. Where are you? Arc cotangent, however, okay, arc cotangent, that was a little tricky. Okay, because this software doesn't produce it. But no fear, I have one for you, so I'm going to put it together for you. And it has a horizontal asymptotes, okay. One is a negative pi over 2. And make it a broken line. And the next one is pi over 2. So that's the horizontal weight. How come it doesn't show? Oh, it's my fault. Because I need to make it, I need to 5. Wait. Okay, it's a range thing. Okay, there you go. Okay, so here we get the arc sine. Okay, so that curve, it's right there. Okay, that's the arc sine. Arc cosine, don't worry about arc cosine. Okay, because this software doesn't graph it, but I will get it for you. At first, we write it down, arc, because it's not often used, that's why. Okay, it's not often used, or it's not used as much. Okay, so let me first put in this, so arc cotangent. Okay, arc cotangent produces angle, and the range is 0 to pi. Okay, wait. Okay, the range is 0 to pi. And the inequality form, okay, domain the same. The inequality form, the absolute value form is such. Okay, domain is all real numbers. And the inequality form in absolute value or inequality form are these. So arc cotangent, I think I have a picture. I'm just going to bring it back. Okay, so arc cotangent. I have a picture, didn't I? Okay, at the time we talk about these things. So I'm just going to bring that picture with us. That was arctan. That's arctan. Where's my arc cotangent? What did I do it with the, that was arctan. Come on. Okay, sorry, let me find it from another place. Okay, arc cotangent, I must have it here. Okay, at O trig summary. At O trig summary. This is it. Okay, this is the place. This is the place. So I'm going to take this picture to fill that gap. Okay. So this is our arc cotangent. And in terms of the truncate, it's the same as cosine. Okay, so we chopped off quadrant 3 and quadrant, wait, the software is not moving. Wait, is it freezing? I first run to save it. There. Come on, guys. What's going on? Wait. Okay. All right, that's not the end of the world. I found it. Okay, so let me give you a smaller version of it so we can see more. Okay, so the arc cosine with the, no fly zone indicated, arc sine, arc cosine, all forms of domain and range. All form and domain and range. Let me just make it a little larger so you can take the notes. You can take the notes here. Wait, 125%. Yeah, that would do the work. Yes, you can see everything clearly. So this is arc sine, the purple, the arc cosine, arctan, all forms are given to you, okay? Interval form, absolute value, inequality form, arc cotangent, all the forms are given to you, Okay, all the forms are given to you. So now we have these basic information. We have these very basic information. What do we use them for, right? What do we use them for? Well, one of the applications we're going to use them for is to determine domains of more complicated functions. Domain of more complicated functions. Let's see, is this lecture too long? This lecture too long. So this lecture has been, okay, I think we can still talk about some examples. Okay, so with all of these summarized, okay, we're going to start talking about examples as how do we apply them. Examples, application to domain determination. Okay, so let's look at some examples for determining the domain. Okay. The first one. Okay, the first one. We have a function f of x equals to 2 minus x. You can see, obviously, this is a one function subtract the other, right? A constant function minus another function. We know this is a new function. This new function is a rule. And obviously, this is also, you can see it from many different perspectives, okay? The first perspective I would take you guys to see is that we studied these functions, right? So it's a combination of these two. It's a combination of these two, right? It's one function subtract the other function. We know that one function minus another function is, so first point of view, okay, so I'm going to put a note here. It can be seen as the difference of two functions. What are these two functions? I can see this one function as g function, which is 2, constant function, and another function is h function, right? H function, which is the, it's equals to x, and f of x is just equals to g function minus h function. So this is the perspective you probably have never thought of, right? That's one perspective. Okay, that's one perspective. What are the other perspective? The other perspective, if you remember, you learned y equals to mx plus b, right? This is a linear function. This is a linear function, right? So this case is actually a linear function in what way? Our function here is basically y equals to negative x plus 2. So it's a linear function, okay? It is a linear function. And if you still remember polynomial, it is a polynomial. It's actually a binomial. So you can see it from many different perspectives, but we are just to determine its domain, right? So what's the domain for this constant function? All real numbers. What's the domain for this function? All real numbers. Therefore, the domain, okay, it doesn't really take that much effort. For the domain goals, the domain is just all real numbers. The domain is all real numbers, and we can even graph it pretty easily, right? if we know y equals mx plus b, it's pretty easy to graph this. You just need to plot 2 points. Or in these days and time, it's at your fingertips to graph this function, domain and range, right? The range is not asked for, but the range is all real numbers as well. It's all real numbers as well. It didn't ask for graph, so we just skip it here. We just skip it here. So let's look at another function. Let's look at another function. So make it A, B, C. Okay, let's look at the second example. Second example, f of x equals to x squared minus 2x plus 1. What's the domain of that? I would still like to talk about perspective, because in the future, when you take calculus class, right, you're going to learn a bunch of theorems. You say, how does the theorem apply to my situation? Right? How does the theorem apply to my situation? One of the perspective is that this is a function, right? You see, we have g and h, right? So we have these functions in the previous question, right? So put a note here, okay? This is really just perspective, the function perspective. Okay, perspective, the function perspective. The function perspective. So this is our g, right? And that's our x. So I'm going to make g equals to 1. How about that? Right? It's a constant function too. And could I introduce another function? Yes, a k function, right? K function. K function, I'm going to have x squared. And these are the 3 kinds of functions we studied earlier on, didn't we? Right? Constant function, linear function, square function. Where is my square function? Right here. Right here. X squared, right? So you can see it from that perspective. But what is f of x? F of x is really what? It's a k of x, right? Minus 2 times h of x, right? 2 times x, and plus a g function, plus a g of x, right? So this one function we see here can be some kind of combination of 3 other simpler functions. And we call these basic functions, okay? So from that perspective, I'm introducing that, you know, all these functions can be broken down and classified into the most simple forms. And at the simplest form, we study them and then we build them up. Okay, so that's the other perspective. But anyway, in most of the other courses, we don't talk about these things. But I want to talk about these things because I see you guys getting into calculus classes, and you might need one day the decomposition of functions. You need to break complicated functions into smaller pieces and simpler functions. Okay. Now, domain, in this case, is actually a quadratic function, right? This is a quadratic function. So even though I gave this perspective, but this function is really just a quadratic function. It's a quadratic function. What is a quadratic function? Quadratic function is in this form, okay? It's ax squared plus bx plus c, where a is not 0. That's a quadratic function form. Quadratic function form. Okay, so this is one of those functions. Quadratic function, the domain, all real numbers. All real numbers. How about range? Is the range going to be all real numbers? Actually, it's not necessarily. In the future, we're going to talk about how do we determine the range of quadratic function. And for now, we're not asked about quadratic function. Therefore, we're not going to get to it. We're not going to get to it. Okay. So it's a quadratic function. Quadratic function. Okay. So all the things you've seen before, they all have some kind of function perspective. They all have some function perspective. Okay, I wish you know that. Okay, streamlined. So that's a domain. So let's look at another situation. 3. Okay, we're still going to determine the domain. And that is, this function is 1 over 3x minus 1. 1 over 3x minus 1. What kind of function is this? Does it have anything to do with what, our basic functions? Absolutely. Where's our reciprocal function? What is our reciprocal function? This guy, right? 1 over x. So how do we see, how is this function? So if we see the function perspective, right? Or operations of function perspective, what would it be? Well, we can see a g function as 1 over x, right? And h function, and it's going to be 3x minus 1. How about that? Right? So, and f of x is going to be what? Is g composite h. Do you think it's going to work? Do you think it's going to work? G of h of function. And that is going to be what? That is going to be what? That's going to be g of h of x is 3x minus 1. And the composition will lead us to 1 over 3x minus 1. This perspective is very important in the future when you're taking calculus classes. Okay, you will need these composition and decomposition. Okay, so this process we just did is decomposition. So you decompose it into two simpler functions. Okay, so that's one important perspective. I think these are the perks I'm giving you guys, okay, to better prepare you for your calculus classes. So please do pay attention, okay? Please do pay attention, practice. If you have any questions, get back to me. And of course, in this perspective, we just want to make sure the denominator is not 0. So to determine domain, right? We just have to say, oh, there are 2 ways of setting this up. Okay, set up. Okay, one way is say 3x equal to 0. And then you solve for x. And x equals to 1/3. Okay, because we cannot allow 0 denominator. So any number that make the denominator equal to 0, we have to rule them out. So when we illustrate the domain, we will say x not equals to 1/3. The meaning is all real numbers except 1/3. That's what it means, okay? Another way to set up is to say, hey, the denominator is 3x minus 1. It cannot be 0. And then we're solving for x, that x cannot be. And of course, we still get x cannot be 1/3. So it's two statements. One you say it's just say if this is 0, that's not allowed. And this one is saying a denominator cannot be 0. They're saying the same thing, right? So in the first setup, we're trying to say, you know, we're going to identify all the numbers that is going to cause the denominator equals to 0 and remove them from all real numbers. And the second one is just more straightforward. So either way works, but you have to be clear about what you're doing. Okay, so let's look at number 4. Number 4, we have a situation which is f of x is equals to cubic root of x and x squared plus 1. And of course, we can see this is going to be some kind of composition of functions, right? We can see this as a composition of functions for sure. Oh, wait a minute. Where's my composition there? Okay, so I should put these together with that relevant function, okay? All right, so let's look at the next one. So what kind of composition would that be? What kind of composition would this be, right? To compose this, right? You have to think backward, right? So how do I make that a composition? We certainly need the reciprocal function, right? We need the reciprocal function. And what else do we need? We need a division of functions, don't we? Okay, so I'm gonna call g of x equals to the root 3 cubic root function. Okay, and my h function, I'm going to make it h1 over x, the reciprocal function. You see that function is very useful. Okay, my k function is going to be x squared plus 1. Okay, so let's see how we're going to compose it, right? How do we compose GHK? Okay, let's do it for fun. Okay, let's do it for the fun of it. So H composite K, right? K of x, that's going to be what? That's going to be H of K of x. Okay, and that's going to be HK, which is x squared plus 1. Hold on. X squared plus 1. And now it's equals to 1, and H, that's going to be 1 over that x squared plus 1. Right? So what can f of x make? Eventually, f of x is going to be what? Is g of x multiply this piece. multiply that guy. Right? Multiplication of functions. So in the end, we have this guy. And the numerator is going to be the cubic root function. Okay. We're not going to do this all the time because it's we're going to have another setting. We're going to focus on doing these sort of things, but just give you some give you some material for your thoughts. After all, we want to determine the domain of this function. Well, cubic root function, this has domain of all real numbers and ranges all real numbers, and it's in the numerator, so it can be any number. Denominator cannot be 0, but x squared plus 1 is always at least 1, right? It will never be 0. Therefore, the domain is actually all real numbers. Because when you ask for x squared plus 1 not equal to 0, it's always true. It is always true. Okay. So, all right. So we're dealing with these domains of function. And let's look at another one. Let's look at another one. Okay. These are related to trig functions. Trig functions. Okay. So I'm going to give you a number 5, right? And I have a function here. It's a cosine x over 1 minus sine x. What is the domain? What is the domain? Right? We are to find the domain. What is the domain? Cosine x has a domain of all real numbers, and cosine x is in the numerator, so it can be any real number. And even though cosine x is, it has a range. Denominator, however, right? Denominator cannot be 0, so we set it equal to 0. So I know to see what it's going to take us to. If it is 0, what's going to happen? Sine x will equals to 1, right? We're thinking of all the real numbers that x cannot be, or x can be, to make it equals to 1, and those numbers must be excluded from the domain for this function. So what are those numbers? What is sine x equals? What makes sine x equals 1? What makes sine x equals to 1? Yeah? All right, so what have we learned? What have we learned about sine x? Didn't we have that? Yeah, we can use a unit circle. We can use unit circle. Certainly, we can use that unit circle, right? In this case, where all real numbers are considered. All real numbers are considered, right? So on the unit circle, what will make sine x equals to 1? Look at that unit circle. What will make sine x equals to 1? Which terminal will give sine x equals to 1? Sine x are sine value are the blue numbers, right? And so this is the number, isn't it? Right here, right? So which terminal is this terminal? Yeah. So this is the terminal that it cannot be. This terminal that cannot be. If it is pi over 2, 5 pi over 2, right? So you're gonna figure out it cannot be what? It cannot be pi over 2, right? It cannot be negative 3 pi over 2, right? It cannot be 5 pi over 2. So what it cannot be? Yeah. So let's think about the angle measurement. Think about angle measurement. What will cause x equals to sine x equals to 1? What would that be? Pi over 2 will cause it, right? Let's do one by one so we can find a pattern. 5 pi over 2, right? 5 pi over 2. What else? Pi over 2, what? 5 pi over 2 is pi over 2 plus 2 pi, right? Plus 2 pi. And if we plus another 2 pi plus 4 pi, we'll get another one that cannot be. That will make this happen, right? So it's 4 pi. Right? So multiples of 2 pi. And we also talk about there could be negative numbers too, right? There could be negative. What are the negative? A clockwise measurement. Negative 3 pi over 2, right? Negative 3 pi over 2. And what else? And negative 3 pi over 2 plus what? Plus 2 pi. Right? Or plus 4 pi. Have we found a pattern? Have we found a pattern? Found a pattern. Is there a pattern? Is there a pattern? On all of these, right? Obviously, we have a pattern which is pi over 2 plus 2k pi, right? On all of these, what is the pattern? Negative 3 pi over 2 plus 2k pi. Okay. Do these two have anything in common? Do these have anything in common? 2k pi is a common, right? Can negative 2 pi be written as negative pi over 2 minus pi plus 2k pi? Can we do that? Yes. So this will be pi over 2 plus 2k pi. This is just a bunch of algebraic manipulation. And over here, we have a negative pi over 2 plus, if we combine these two, right, we have 2k minus 1 times pi. Right, 2k minus 1 times pi. So is a positive pi, negative pi, and positive pi over 2, negative pi over 2 plus multiples of 2 pi or odd number multiples of pi. So how do we express it? It looks like we need two expressions to express them, right? So it just exclude the pi over 2 terminal. Just exclude the that terminal. So we're gonna take this guy. Okay, we say for that, if this is true, then x has to be, wait, x is going to be equals to pi over 2 plus 2k pi, or x equals to, let's take this one, simpler. Okay, because I don't think we can have any, one form. Okay, so just leave it, just keep it simple. Just keep it simple for now. Okay, just keep it simple for now. And I don't want to work you guys up on the algebraic manipulation yet. Okay, so these are the values that must be excluded from the domain. So when we're stating the domain, we will say x cannot be that, it cannot be that. Those are the values x cannot be. Okay, pi over 2. Okay, plus multiples of 2 pi, or negative pi over 3 pi over 2 plus multiples of 2 pi. And k is any integer, Okay, so determining the domain, you can see it utilizes, some familiar techniques. So here, I'm gonna put it as think out aloud. Okay, what you do on the scratch paper. Okay. Let's look at another example. Okay, let's look at another example. Determining the domain of a trig function. Okay, so this should be number 6. Okay, this will be number 6. And the question is g of x equals to 1 over 1 minus tangent x. We are to determine the domain. And obviously 1 minus tangent x cannot be 0, right? So if we set it equal to 0, whatever solution we get, and we have to exclude those numbers, right? So if tangent equals to 1, right, the next step we get tangent equals to 1. So tangent x equals 1. So what are the values? What are the angles that will cause tangent equals to 1? We know tangent has its own domains, right? Which cannot be odd number multiples of pi over 2. So in addition to that, tangent x equals to 1. So what are those terminals? That's right. So this terminal, right? And that terminal. Okay. So what x cannot be? Well, what x can be? What is the solution to it? Right? Obviously, x cannot be what? X can be pi over 4, right? To make that true. We're looking for solution to make this true, okay? Forget about domain yet. Pi over 4. We plus pi, we get 5 pi over 4, right? So plus k pi. Right? You see, this it cannot be. This is the solution, and plus pi, you get another one. You plus another pi, plus another pi, plus another pi, plus another pi. You keep adding pi. So those are multiples of pi's. Those are the terminals that will cause tangent x equals to 1. Right? So pi over 4 plus k pi. So now what's the domain? domain would be x cannot be any real number, but that in addition to the domain, of course, right? In addition to the domain, in addition to the domain requirement for tangent, right? When we're doing this, obviously we're doing this in the domain. We're doing it in the domain. All right, so let's see. So we have a tangent. Let's do one more, maybe two more. Okay, two more. 22. Not just to, not actually. Yeah, I'm looking at some look at my notes. There should be number 7. Okay, the function at hand is f of x equals to cosine x divided by 2 plus sine x. What will be the domain? Numerator, it can be anything. Denominator cannot be 0. How can we guarantee denominator is not 0? So when will the denominator equals to 0? Right? Any number that makes the denominator equals to 0, those numbers will be excluded from the domain. So what are those numbers? This is the moment we get to use the domain for sine x, the range for sine x. Sine x is between -1 to +1 for any real numbers. For any real numbers. So this piece is never going to be 0. There's no solution, not possible. Okay, so this will never be 0. And therefore, the domain is what? The domain for this function is from -∞ to +∞. Yes, all real numbers. Okay. Last but not least. Okay, trig function related to determine domain. And this is sine x 1 plus cosine x. This time, denominator may be 0, right? Because cosine x, the range of cosine x is what? From -1 to +1 inclusive. So cosine x equals to 1 is -1 is possible. So we're going to set 1 plus cosine x equals to 0. We're going to find what value will cause the denominator equals to 0 and exclude those numbers from the domain. Okay, so that's our objective. So let's see what we get. If 1 plus cosine x is 0, that means cosine x equals to -1. When will cosine x equals to -1? When will that happen? The red number, right? This red number is +1. Which red number is -1? Right here. And none of the other red numbers are -1. So this terminal that x cannot end up here. Whether you measure counterclockwise or clockwise, anywhere you go, it cannot terminate there, right? So what are the features about these points? Okay, these angles, sorry. What are these angles x can be? X can be what? Can be pi. It can be negative pi too, so plus minus pi, right? And plus minus what? 3 pi, right? And plus minus what? 5 pi. And so on and so forth. So basically x is what? Is odd number multiples of 2k plus 1 multiples of pi. And k are integers. Right? Plus 1 minus 1 plus 2 minus 2, plus 3 minus 3, plus 5 minus 5. Could it be 0? It cannot be 0, right? You see, it doesn't include 0. Cosine 0 is a positive 1. So it's odd number multiples of pi. Will this ever be 0? No, it will not be, right? If k equals to 1, k equals to negative 1, yeah, so that's odd number multiples of pi. So in the end, the domain is what? Domain is x cannot be odd number multiples of pi. Odd number multiples. This is the odd number multiples of pi. Okay, we have done plenty. We have done some examples about domain and range for trig functions. And so we did some rational functions, we did some, other miscellaneous functions, and you have homework, so please pay attention to them. Let's look at just another example. Okay, just another example. Number 9. G of x. Okay. This function is ln x minus 1 and minus 1 outside. What is the domain? This requires us to know what's the domain for the logarithm functions, which we studied, right, and reviewed. We studied and reviewed. Where is it? I'm looking for it. ln x, domain and range, right? Domain and range. So ln x domain is larger than 0. Larger than 0. So here we have a ln x, right? And in the place of x, there's a x minus 1. That's our situation. That's our situation. Okay, so at whatever follows, so this baloney, right? So this piece, the domain has, this piece, the omega has to be positive. So now we have x minus 1. So x minus 1 must be positive. Okay. And this minus 1 is outside because the order of operation determines we're going to do this piece first. So we will have an output. After we get the output, which is any real number, we subtract by 1. So that's not a problem. So we just have to guarantee that the domain is that requirement is satisfied, which require x minus 1 must be positive. So as a result, x must be larger than 1. So domain is x is larger than 1. So that's the domain for that function. For that function. All right, I think this is enough for this lesson. We have more than 1 hour already. And I will see you in the next lesson. We will continue to review our material in the past 7 weeks and see them in the light of application. Okay, in the light of application. Thank you for watching. Until next time. Have a great day.